Okay, this is the video for section 3.2, Graphs of Equations. We're going to be looking at the pre-class notes. Remember, these were not specifically attached to the ones for 3.2 circles, which is what we already started in class. So we're going to learn how to use a table of values to graph an equation, find x and y intercepts algebraically, and determine whether an equation has an x-axis, y-axis, or origin symmetry. Okay, so things we need to talk about. Two quantities are sometimes related by means of an equation or a formula that involves usually two variables or more. In this section, we're going to discuss how to represent such an equation geometrically by a graph in a coordinate plane. The graph may then be used to discover properties of the quantities that are not evident from the equation alone, and just some things that we need to remember. And a solution to an equation that has two variables, an x and a y, will be an ordered pair. X always comes first, y always comes second. So you can check if something is a solution by plugging it in for the letters x and y respectively and seeing if the left side equals the right. And then each ordered pair we get is part of a solution set, so that means all of those points, any ordered pair that makes the equation true, if you were to plot all of those, that is considered to be the graph of the equation. So sometimes one of the easiest ways, if you've never encountered a graph before, if you don't know what the shape is to do what we call a table of values. The problem is the more complicated the equations get, plotting points may not give you enough details about the actual shape, so we'll obviously learn more sophisticated methods. A shape that you might be familiar with is a parabola. Parabolas come from when you have x squared in your equation. For example, this equation is y equals x squared minus 3. You don't have to know that from the picture, but that is the represented picture here. The lowest point in this graph is 0, -3, and the lowest or highest point in a parabola is always called the vertex. We will have a whole section 3.6 dedicated to talking about parabolas and their vertex. Okay, so x-intercepts are where you cross the x-axis. They are always points that look like this, a number, comma, 0. Y-intercepts are where you cross the y-axis, and it's always 0, comma, a number. We're just using A and B as generic letters. If you want to find your intercepts algebraically, you just think about what the ordered pair looks like. There's a 0 in one spot and none in the other. So if you plug in 0 for y, you can find the x-intercepts. If you plug in 0 for x, you can find the y-intercepts. Don't forget to write them as ordered pairs. Another thing we're going to talk about in this pre-video is symmetry. Symmetry means that it's almost like the butterfly effect where you fold a butterfly in half and it matches on both sides. This right here has y-axis symmetry because notice this matches across here. If you folded this down the y-axis as a piece of paper, those two sides would match up. Notice that when you have y-axis symmetry, the only difference in the ordered pairs is that the x changes signs. So a parabola is definitely a good option for y-axis symmetry. To have x-axis symmetry, notice that you have to be able to fold it over the x-axis. What changes here is that the y changes signs. Notice now it's not y equals x squared, it's x equals y squared. So that gives you a parabola on its side. And then lastly, the last type of symmetry that you can have that we're concerned with is called origin symmetry. So notice origin symmetry is a double fold. You fold over the y-axis and then you fold upside down over the x-axis, noting that both x and y change signs. So if this was the ordered pair 1, 1, -1, -1 would be the ordered pair down here. A common one that has this kind of symmetry is things with x cubed in it. Not the only type, but it's a common one that has origin symmetry. Okay, so to test for symmetry algebraically, because you won't always have a picture in front of you, If you want to test for x-axis, you replace y with negative y, you simplify the equation down, and you check to see if the original equation pops back out. So obviously when we say work it out, we're talking about if you cube it, you have to cube the sign, so you have to see if it comes out to the original. And I'll do one of these. So y-axis symmetry, you need to replace x with negative x and simplify, see if the original equation comes out. And to test for origin symmetry, you replace both x and y with negatives, and then work it out to see if the original comes out. Okay, so this is the example we're going to be doing. It has quite a few. We're going to be graphing these using a table of values. We're going to find our x and y intercepts and label them on the picture. And then we're going to use our test for symmetry, and we're going to make sure that the algebraic way of testing matches with the picture. So for this first one, we're going to do a table of values. If you don't know what points to pick, usually safe ones are -2, -1, 0, 1, and 2. That will not always work for you. So sometimes there are hints about what you should pick, so I'll show you that in a minute. So if we plug in -2, 3 times -2 would be -6, plus 2 would be -4. Plug in -1, 3 times -1 is -3, plus 2 would be -1. 3 times 0 is 0, plus 2 is 2. 3 times 1 is 3, plus 2 would be 5. And 3 times 2 is 6, plus 2 more is 8. So we're going to plot that over here, -2, -4, -1, -1. Oh, my -2, -4 didn't stay on there. It's not wanting to stay a little bit. There we go. And then we have 0, 2. And then we have 1, 5. And then we have 2, 8. Now, if we wanted to draw this line, since I have a line shape, I'm going to draw that with that. We would draw a line that connects all of those points together, and the arrows means that it continues on forever. Now notice this does have an x-intercept and it does have a y-intercept. We would want to find those algebraically though because, mainly because we have a problem with the way this one crosses the x-axis. It's hard to tell where that is. So we get off that shape. There we go. So if we want to find our intercepts, to find the x-intercept, you plug in 0 for y. So that would be 0 equals 3x plus 2. We would subtract 2 over, divide by 3, and remember, write this as an ordered pair. -2/3 for x and 0 for y. For the y-intercept, we already know what it is. 0, 2 has to be the y-intercept, and you can physically see that. So if it's that simple, go ahead and just write it. For symmetry, so this is what I meant by testing for symmetry. You have to do 3 different tests. X-axis. The way you test for x-axis is you change all of the y's to negative y's. Then you try to get this to look like the original. So to get it to look like the original, you'd have to divide everything by -1 to get that negative to go away. Once that y looks like the original y, the question, oh sorry, this is supposed to be a negative over there. Just going to mark that out. I divided everything by -1. Once you've done that, once the left side looks like its original, if the right side does not also look like the original, then it does not have that symmetry. So, and you can tell that if you look at this, if you tried to fold it over the x-axis, they wouldn't match up. One would be going this way and the other one would be going that way. So then we want to test for y-axis symmetry. This time you change the x to a negative x. And to work it out, you just have to say, well, what is 3 times -x? And again, the left side looks like the original, but the right side does not, and there's nothing we can do to fix that. So this is a no. And then the final test is the origin test, where you change both y and x to negatives. That would be -y equals -3x plus 2. I would divide everything by -1. And again, everything looks good except for that -2 at the end. So this one has, and it doesn't look like this folds in any kind of symmetry ways that we were talking about. So no symmetries that we were concerned with, intercepts, and the graph. Okay, let's try one that's a little more interesting. Okay, when you're dealing with parabolas, it gets really difficult to, if you don't know much about tables of values, to know if you've picked the right point. So if you have factors first, I would do that first and go ahead and find your intercepts. So x, let's see, -40 would be 8 and 5. So -8 and +5. So that would be x equals 8 and x equals -5 if we let that be a 0. So if we let this be 0 equals those. So that means we have two x-intercepts in this parabola, 8, 0 and -5, 0. The y-intercept is going to be really big, or small I should say, because you say y equals, and then you let all of the x's be 0, just like we did a minute ago. That just leaves you with -40. So that would be 0, -40, which we're not going to be able to graph. We're just going to have to put a point really low and say that. That's a y equals. Okay, so the reason I did those first instead of my table of values is I'm going to go ahead and plot those x-intercepts. And notice that wherever your two x-intercepts are, that means your parabola is happening in between those. So some good points to try to plug in might not be -2, -1, 0, 1, and 2, because that's going to be kind of off-centered. Maybe I want to try to grab 3 points in the middle somewhere. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a distance of 13 between those. So maybe I want to do 0, 1, and 2. Those kind of look more like they're in the center to get the rest of this graph. So sometimes doing the intercepts first will help. Oh, we already did 0. Let's do 1, 2, and 3. Okay, so if we plug in 1, 1 squared is 1. So I'm just plugging it into the equation. So 1 squared is 1 minus 3 times 1. So that's 1 minus 3 minus 40. That is -43, and that'd be -42. Okay, let's try 2. 2 squared minus 3 times 2 minus 40. Let's see. That would be 4 minus 6 minus 40. That is also -42. And that tells me something right there. That means my vertex is probably going to happen right halfway between those. So that'll be, because this is exactly the same on both sides, which means we went a little bit lower somewhere in halfway between. Because parabolas go down and they come back up. And then 3 squared minus 3 times 3 minus 40. That's 9 minus 40. That would just be -40. So see, we're coming back up. Okay, so since this is so off-skewed here, I'm actually going to change the scale that we are graphing this for the y-axis. Let's change this to counting by, let's say, tens. So that'd be -10, -20, -30, -40, and -50. Okay, so 0 was -40. 1 would be -42. 2 would also be -42. So remember I said there's something below here a little bit. And 3 would be -40. So notice this is a very wide parabola. I'm drawing this the best that I can on this thing. Okay, the symmetry test. For this one, we would say and I obviously see that this doesn't, it has symmetry, but it's not around any of the axes or the origin. So I'm expecting this to fail all 3 tests, but I want to show you that. So we plug in a -y when you want to do the x-axis symmetry. When you go to divide that out so that it turns back into a positive like the original, everything else on the other side changes signs. So if everything changes signs on the other side and it doesn't look like the original over there, then it fails the test. We also want to do y-axis and origin. So for y-axis symmetry, you change all of the x's to negatives. Be careful with the one that's being squared. It is negative x squared. This would be negative times negative is a positive. Negative times negative is a positive. And we came really close. The problem is the 3 was negative in the original, and it's positive now once we applied the negative x in there. So this is also a no. And then the origin symmetry. So we change both negative y and negative x. So this would be negative y, that's positive x squared, positive 3x, and minus 40. Divide everything by negative 1 to get y back to being positive, and you'll notice that all 2 of our signs on the right side don't match the original. So this is also a no. We are going to see one in just a second that has a symmetry that it actually passes. Okay, so let's look at C. This one would be probably easy to do a table of values on. I think we're okay with just doing -2, -1, 0, 1, and 2. We'll see if it's enough. You can always plot more points. That's the nice thing about tables of values. So negative, be careful here, this is -2 squared. That does not cancel and make a positive. You have to square it first. That's -4 plus 2. So that would be -2. -1 squared plus 2. That would be +1 plus 2. So then negative times +1 is negative. So that would be just 1, because you're going to get -1 plus 2 is 1. -0 squared plus 2. 0 times anything is 0. So that's just going to be 2. +1 squared plus 2. That'd be just -1 plus 2, which is 1. And -2 squared plus 2. And that gives me -2 again. So let's go ahead and plot what we have so far. So this is -2, -2, -1, +1, 0, +2, 1, 1, and then 2, -2. Looks like we have enough to draw our shape. I also know that my y-intercept is 0, 2, because that came out while we were doing our table of values. We need to find our x-intercept. So plug in 0 for y. Try to solve. So I'd add x squared over. Take the square root of both sides. So it's plus or minus the square root of 2. So square root of 2, 0, and negative square root of 2, 0. Notice that's kind of right because they cross between 1 and 2, which square root of 2 is between 1 and 2 if you use your calculator. And then we want to test for symmetries. This one should have the y-axis symmetry because notice right down the middle, this splits across the y-axis. But we're going to test for all 3. So x-axis, change the y to a -y, change nothing else. Solve for y being positive like we would normally have, and you notice that the signs on the other side change, so that doesn't work. Test for y-axis symmetry. Change the x to a -x. Now this is -x squared. You have to do the order of operations. So you square this negative first, so that just makes it positive, but then you have that negative out front. So notice in this case, this is the original equation. Nothing changed by changing that sign because it got squared. So this does have y-axis symmetry. And it should fail the origin symmetry just based on the way it looks. So -y equals -x squared plus 2. You change both to negatives. Go ahead and work out the right side first. That would be negative squared is a positive. Bring in the negative down front. Divide everything by the -1 to make the y positive. And again, your signs change to the wrong way. So this one had one symmetry but not the other. Okay, so we have 3 more graphs. I'm not going to go through the heavy detail of all the symmetries. For testing, we're just going to look at the pictures because I think you kind of get the gist. It's just an algebraic manipulation. We don't put that on the test. The only thing on the test is if you have a picture in front of you, can you tell me which symmetry you have? So that's why I said it's more good to know how to do it from, or better to do it from the picture. So let's do this one. This one's a little tricky for students because this time the x is by itself. So if that ever happens, pick your y's instead and then plug in to get your x's. So we can try the -1, -2, 0, 1, and 2, but we're plugging them in for y. So I'll work that out. So that would be -2 squared is 4 times 2 is 8 minus 4, so that would be 4. Then we plug in -1. -1 squared is 1 times 2 is 2. 2 minus 4 is -2. Let's see. 0, so 2 times 0 squared. 0 times anything is 0, so this is just -4. Let's do 1. 2 times 1 squared. That would be 2 times 1. So that's just 2 times 1 minus 4 would be -2. And 2 times 2 squared. 2 squared is 4 times 2 more is 8 minus 4 is 4. So let's plot what we have. 4, remember these are the x values. 4, -2, -2, -1, -4, 0, -2, +1, and +4, +2. So again, remember this has the y being squared, so we get a parabola on its side. Okay, so it looks like we can clearly see our x-intercept is -4, 0. The question is, what is our y-intercepts? Because I don't know for sure that I drew that pretty or not. So if you want y-intercepts, plug in 0 for x. This is how you would do it algebraically. Add the 4 over, divide by 2, and take the square root to get rid of that squared. So it looks like we have 0 square root of 2 and 0 negative square root of 2, which makes sense. They're kind of between 1 and 2, just like the last graph. And then just looking at the picture, because like I said, that's all you're going to be given in a testing situation, but it's nice to know how to test for symmetry algebraically. This is folded right on the x-axis. So this one is going to have x-axis symmetry. Okay, let's do this one. So 1/2 x to the 3rd power. So I'm going to try my tried old true -2, -1, 0, 1, and 2. Plugging in for x this time because y is by itself. So 1/2 of -2 cubed would be, that's -8, so half of -8 is -4. 1/2 of -1 cubed, well, that's 1/2 of -1, so that's just -1/2. 1/2 of 0 cubed would be 1/2 of 0, so that's just 0. And 1/2 of 1 cubed would be +1/2. And 1/2 of +2 cubed would be 1/2 of +8, so that is going to also be 4. So same similarities kind of here, but this is a negative and this is a positive because cubes keep their signs. So -2, -4, -1, -1/2, 0, 0, 1/2, and 2, 4. With cubes, it looks like a parabola that has a split personality. Half of it goes down and half of it goes up. So this is going to have origin symmetry because note that this point right here, 1, 1/2, we also have -1, -1/2. Both signs changed. So it's like flipping it over and then flipping it down. And the x and y-intercept, the only thing we have is the origin, so it's the same. Anytime you're at the origin, you are both an x-intercept and a y-intercept at the same time. And then our last one for section 3.4. This one is a square root. You have to know something about square roots. This part right here has to stay greater than or equal to 0, or you'd have an imaginary number. So the way to do this is to set this inside part greater than or equal to 0, and that tells you that if you add that 4 over, you cannot plug any x values in that are less than 4, or your graph will have an imaginary number, and we don't graph those in real numbers. So this would be, I would start with 4, and let's just do 5, and let's see, I wouldn't plug in 6 because that would give me square root of 2. 7 would give me square root of 3. 8 would work because we'd get a square root of 4 because 8 minus 4. So 4 minus 4 would be square root of 0, which is just 0. 5 minus 4 would be square root of 1, which is 1. And 8 minus 4 would be square root of 4, which is 2. So 4, 0, 5, 1, and 8, 2. Notice that this square root looks kind of like the parabola that was on its side, but it only has half of it. And that's because we're taking a square root and they did not write plus or minus in front. If they had a minus part in front of the square root, you'd get the same shape but down here. So interesting to note, and something we'll talk about a little bit more in section 3.5. Right now we're just getting our feet wet with graphing. So x-intercept is 4, 0. There is no y-intercept. We do not get a y-intercept because we can never plug anything in less than 4. Otherwise, we would be imaginary. And then no symmetries. To have symmetry, you have to have something to mirror on some other side. Okay, so that's the end of the 3.2 pre-notes.